Okay, so lecture 8, domains and arithmetic of functions. In this lecture, we'll talk about domain in word problems, domain for functions that that's not a word problem, and some stuff about arithmetic of functions. And arithmetic means addition and subtraction, multiplication and division. So here's Bob's Donut Shop, fixed cost of $3,000 each month, variable cost of 75 cents per donut, or $0.75. He can make up to 15,000 donuts each month, sells them $1.25 each. So what's his cost function? So we need variables, and X is number of donuts made, and we're assuming that he sells all the donuts that he makes, right? There is a problem here about storing stuff. And about what do you do with donuts that you make that you can't sell, but we're just going to start with, we're assuming that he can sell all the donuts that he makes. So what's his cost function? Cost depends on how many donuts he makes, right? So cost is the function, depends on the number of donuts he makes. 75 cents times the number of donuts plus 3,000. Revenue function. Revenue is money coming in. So REV of X, there's my name and of the function, and there's my variable X. So revenue depends on how many donuts that he sold. That's what X stands for, and $1.25 per donut. So 125X. Great. So what's the domain of each function? Domain is what are the restrictions on X, right? How many donuts can he make, can he sell? So his store can make up to 15,000 donuts. So his domain is going to be 0 less than or equal to X less than or equal to 15,000, right? I'm using X here to stand for number of donuts made, or in an interval notation, this. Technically, of course, it's only integers between this. He can make 0 or 1 or 2 or 3 or 4 or 5. But we're going to let that slide and just assume all numbers between 0 and 15,000. Units of slope. Is dollars per donut for both of them, right? $0.75 per donut. Selling his donuts, the 1.25, the units of slope, he sells them at $1 each, so dollars per donut. So units of slope are almost always this for that. Cost is measured in dollars, revenue is measured in dollars, so it's going to be dollars per donut for both of them. Breaking even, how many donuts does he need to make and sell to break even? So remember that breaking even is when your cost function equals your revenue function. That's when 0.75x plus 3,000 equals 1.25x. Subtracting off a 0.75x from both sides gives me 3,000 equals 0.50x, divide by both sides by 0.50, and you get 6,000 equals x. So to break even, right, to have cost equal to revenue, has to make 6,000 donuts. And what's the profit function? So profit function is related to cost and revenue. Profit, and I'll write that as PROF, is money coming in, which is your revenue, minus money going out. And we have to be a little bit careful about how we set this up. Revenue is 1.25x, cost is 0.75x plus 3,000. But I want to subtract off the entire cost function. So I'll throw that in parentheses and put the minus sign in front. So my profit function, his profit function, is 0.50 minus 3,000. Right, 1.25 minus 0.75, that's my 0.50x, and then minus 3,000. Great, so he makes a profit of 50 cents on each donut. If he makes a profit of 50 cents on each donut, how much does he need to make to get his $3,000 on fixed costs back? He needs to make 6,000 donuts, and that's the break-even point that we found. If he makes 6,000 donuts, he's making no profit, but he's breaking even. If he makes more than 6,000 donuts, he will make money. So the X-intercept of the profit function, how do we find the X-intercept of the profit function? We set profit equal to 0. We solve for X. So $6,000 means he's making no 6,000 donuts. That means he's making no profit. If he makes more than 6,000 donuts, he'll make 50 cents on each donut. If he makes less, he'll start losing money. So in this problem, his domain is set up by the constraints of the word problem. His factory can make up to 15,000 donuts. So you look at the word problem and says, okay, 15,000 donuts. The formulas involved, though, don't actually have a whole lot to say specifically about whether or not you're making 15,000 donuts or not. So a little bit of language about business. Revenue is price times quantity sold. Profit is revenue minus cost. Break-even point is when revenue equals cost, which is the same thing which we just saw in the previous example when profit equals 0. So what about mathematical domain? So a word problem might specify the domain of a function, but if you're given the graph of the function, you can read off the domain from the graph. But what if you're given a formula? So what's the procedure for finding the domain of a formula? The domain is all real numbers except for 3 exceptions. You can't divide by 0. So if you've got a fraction, the domain is everything except where the denominator is equal to 0, or the X-intercepts of the denominator. You can't have negative numbers in square roots or in other even roots, so 4th roots, 6th roots, 20th roots. So the domain of square root of f of x is all numbers x, so that the thing inside the square root is greater than or equal to 0. And then finally, there's a third rule that will become important when we deal with logarithms later in the course. You can only have positive numbers in logarithms. So what are the domains of this? So A, we need to use rule 2. Whatever's inside a square root has to be greater than or equal to 0. So 2 minus 3x is inside the square root. It needs to be greater than or equal to 0. We solve that. Add a 3x to both sides, get 2 greater than or equal to 3x, and then divide both sides by 3, get 2/3 greater than or equal to x, or minus infinity up to 2/3. So x has to be less than or equal to 2/3. So we're dealing with any number that's less than or equal to 2/3. B, that's rule 1. If I've got a fraction, I can't include the places where the bottom equals 0 because I'm not allowed to divide by 0. So this is rule 1. So we need to set the bottom of the fraction equal to 0 and then solve for that. I can factor this. This becomes x plus 5 times x minus 2 equals 0. So x equals minus 5, x equals 2 are, oh, that didn't write very well, bad points. Right, because these are the numbers that if you stick them into the denominator, you get division by 0. So the domain for this function is all x except x equals minus 5, x equals 2, or you can write it as minus infinity up to minus 5. But you can't include minus 5, and then minus infinity up to 2. No, minus 5 up to 2, but you cannot include 2, and then open up to 2 to infinity. So you can write the domain either like this for the first one, or you can write it like that. What about the third one, C? Well, C, you have to do both rule 1 and rule 2. So for the square root, we need x minus 3 greater than or equal to 0, or x greater than or equal to 3. For rule 1, which is about dividing, we need x minus 5. We need to solve the denominator equal to 0, which is x equals 5, and that's a bad point. It cannot be in your domain. So what's our domain? It's every number bigger than 3 except for 5. So again, we can write it like that. So you can either write it out in words, or you can write it in as an interval notation. Finally, what about D? There's no square root, so we don't need to use rule 2. There's no division, so we don't need to use rule 1. If those don't apply, what is the domain? Right? If you can't apply either rule 1 or rule 2, the domain is all real numbers. So these are mathematical domains because it's just coming from the definition of the function and just assuming that our x's stand for numbers, and which numbers can we use and which numbers can we not use. The example with Bob's Donut Shop, there's a restriction put on there because you could only make so many donuts, and so the domain was restricted. What about adding and subtracting, multiplying and dividing functions? Although we do have to be a little bit careful about domains. So we have two functions, y equals f of x and y equals g of x. So I'm going to call this one g of x, and the dotted line I will call f of x. So we have this notation, f plus g of x. What does that mean? Well, that's just another notation for f of x plus g of x. It just means plug x into both functions and add them up. So, for example, f plus g of 1 equals what? Well, it's f of 1 plus g of 1, right? Just taking the number 1, plugging it into both functions. So if we go to 1, g of 1 is 1. And f of 1, start at x equals 1, and we go down to the dotted line, is minus 1. So f of 1 plus g of 1 equals 0. So we're just adding up the y values for each one. So what's f plus g of minus 4? Well, that should be f of minus 4 plus g of minus 4. So g of minus 4 is, we go to minus 4. G is this solid line, so g of minus 4 is minus 2. What's f of minus 4? Well, we go to minus 4, and then we go up and down, and we go, whoa, that doesn't work. F of x actually just stops at minus 3. And DNE is a very useful abbreviation in math. I don't know why this equal sign, this suddenly moved way down there. It should be up here. And it means does not exist. Right? There is no f of minus 4 because minus 4 is not in the domain of f of x. So if we actually want to add or subtract or multiply f and g, we can only do it for numbers that are in both domains. Right, so the domain of adding those two functions together is just from -3 to 4, because that's the only place where the numbers x can be plugged into both functions. And so there are other notations. F minus g of x, as you can guess, is a notation for just subtracting the two functions from each other. F times g of x is the notation for multiplying two functions by each other. And they all have the same domain, right? As long as you can plug x into both functions, you can calculate what it is. F divided by g of x is written like that, and that just means the fraction f of x over g of x. So we need to be able to plug x into both functions. So we start with this, but we also need, well, one, the bottom cannot be equal to 0. So g of x is this solid line. When x equals -2, you get 0. So here's the x-intercept for g at -2. We can't plug that into a fraction that's got g on the bottom because that would give us a division by 0. So the domain of the fraction is the common domain of the two functions, which is -3 to 4, but without -2. Because we know that g of -2 equals 0. And so if we plugged in x equals to -2, that would give us a 0 in the denominator. We can't have that. Okay, so domain of functions. If it's not in a word problem, the domain is all real numbers except for square roots and division. And that's our rule 1 and rule 2 above.